Good morning. We're going to talk about forces and vectors this morning. You can see here a picture of the parachute regiment display team as they come into land. They need to know about forces if they're going to land safely. So what exactly is a force? You need to learn this definition inside the yellow box. A force is any influence that causes an object to undergo a specific change. There are three types of change that forces can cause. They can cause things to change speed, they can make an object change its shape, or they can make an object change its direction. We can represent forces with arrows, and you can see here three red arrows, because forces are vectors. A vector is something with a size and a direction. So when we look at the arrow has a length. The longer the arrow, the bigger the force, and also it indicates the direction, whether it's going to the left or whether it's going down or it's slanted up. The direction and the size of the force can be represented with an arrow. There are two basic groups of forces as well. You need to learn these names. You need to know what types of forces belong in which group. The first group are called contact forces. So these are forces that only occur when objects are touching each other. So for example, friction, air resistance, water resistance, lift, upthrust or buoyancy, and normal reaction. Two objects must be in contact with each other for these forces to apply. The other group of forces are called non-contact forces. There are three main examples of these: magnetism, electrostatics, and gravity. Now gravity we sometimes call weight. Now magnets do not need to touch to attract or repel each other. Electrostatics, two objects that are charged, do not need to touch each other for them to experience a force. So we call these non-contact forces. Okay, let's look at these examples of forces. You need to learn these names. You may need to use these names when you write a paragraph explaining some physics. So first of all, let's look at air resistance. Now air resistance is a contact force because when an object moves through the air pushes against that object. So in this example you can see the skydiver, he's falling down, but he experiences the air pushing him upwards. So it slows him down. Air resistance is a force that tries to slow things moving through the air down. The next example is pulling and tension. So here is a tug of war. Each one of these men is pulling backwards. There's a pulling force, and that creates another force in the rope which is called tension. Okay, there is a tension in the rope. Let's look at this force here, electrostatic forces. So if you rub the balloon on your hair, it becomes charged. It might gain a positive charge, and that attracts the hairs across, and you can see the lady's hair is being attracted to the balloon. The balloon will even stick to the wall because it has a charge, and we call that force, the force between charges, is called an electrostatic force. It's a non-contact force. Friction is the force between the tire and the road, or between your feet and the floor, and it helps to push you forward when you're walking. We can create a wheel spin, and the friction there creates a lot of heat and it begins to wear the tire away, and you can see all the smoke there from the tire. The next one I want to look at is upthrust. Now this is a balloon which is floating in the air. It's a hot air balloon. The force that makes it rise is called upthrust. Another name for upthrust is buoyancy. Okay, let's look at the pushing force here. Pretty obvious, you've got two men who are pushing with a force, they're pushing this large box. However, there is also a frictional force which is in the opposite direction. That would be friction, and that's at the base of the box and the floor. So two forces actually in that diagram working in opposite directions. Okay, over here we've got magnetism. There is a gap here, and that's because there is a magnetic force between these two magnetic materials. Now, these two are very closely related to each other. Really, they're the same thing, gravity and weight. I'll put the equal sign in there. The astronaut here is on the moon. He has a very small weight because the moon has a low mass. It's a small object, much smaller than Earth, and there is less gravity on the moon. On Earth there is a very large gravity, so we can draw a bigger arrow here. There's a bigger weight. So weight is what we call the force which actually goes downwards. That's the weight. On the moon, weight is small because gravity is small on the moon. On Earth, weight is large because gravity is large on the Earth. Let's look at this winged bird. All birds have wings. What helps them to fly is an upward force on their wings called lift, and that is created by the pressure difference as the air moves over their wings. So what makes a bird and a plane fly is lift. There's also lift on these aircraft here going up. There is a lift force. Now, the picture of the jet is showing thrust. So here you can see the jet coming out the back, and that creates a thrust force pushing the aircraft forward. So thrust is forward. Sometimes we call it the driving force. It might be worth creating a spider diagram in your book of all the names of these different forces. So we have another one here, normal reaction. Now, normal reaction is the force that stops us falling through the floor. There is a force that the floor pushes up against us, keeps us up, and that's called normal reaction. Magnetic, we've discussed. Friction. Air resistance. Now, another name for air resistance is drag. That's a name that you should use and learn. Upthrust, as I said, also called buoyancy or flotation force. Weight or gravity, they're caused by the same thing. Tension we described in the tug of war with the rope. Now, static or electrostatic, either word is okay. Thrust is sometimes called driving force, and that can push a jet forward, it can push a car forward, it can push any kind of motorized vehicle forwards. Lift is the force which lifts anything with a wing, so a bird or a plane. Push and pull are very, very straightforward. Okay, so how do we measure the size of a force? Well, we can use a very simple device called a Newton meter. You can see two pictures here. The one on the right, the Salter Newton meter, we've got these in school. You can measure the weight of an apple, but you can also measure pulling forces, lots of different types of forces with a simple Newton meter. It has a spring inside of it. You can see the spring in this picture here. There's the spring, and the bigger the force that pulls on here, the more the string stretches, and you will see the marker move further down on the scale, and you can read off the size of the force. The units of force are newtons, capital N. You can just write a single capital N there instead of the whole word, named in honor of Isaac Newton. Now, there are lots of forces that go up, and it's very, very easy to get confused between them. So here we have 5 objects. They've all got the same weight pulling them down, or the same force pulling them down, weight. However, they all have different forces acting on them upwards. So in the first example, the car, the upward force is called normal reaction, because weight pulls us down, but we don't go down towards the center of the earth, because the earth, the surface of the earth, pushes us back up with a force equal to weight called normal reaction. The next example is an aeroplane. As previously described, anything with wings has a lift force, and that is caused by the pressure difference across the wing. The next one is a submarine. Now, we don't think of submarines as floating. They can sink, but they can float upwards as well. So they also have an up thrust force, also known as buoyancy, and anything which floats in the water, whether it's a submarine or a boat or anything else, has an up thrust force acting on it. Now, these next two cause confusion. Many people think balloons and parachutes are the same kind of thing. They're not. A parachute is designed to increase the air resistance or the drag to slow a parachutist down. A parachute will never go upwards. It just slows the descent. The next one, I hope you can see that very clearly, is a balloon. A balloon is floating, and therefore it has an up thrust force. Okay, let's go through this paragraph here, put the correct words in. So bikes, cars and other vehicles experience air resistance as they move. Air resistance is caused by the frictional force of the air against the vehicle. The faster the vehicle moves, the bigger the air resistance becomes. The top speed of a vehicle is reached when the force from the cyclist or engine is balanced by air resistance. We can reduce air resistance by streamlining. So let's fill out the words in this paragraph. Racing cyclists crouch down low on their bikes to reduce the air resistance on them. This helps them to cycle faster. They also wear streamlined helmets. These have special smooth shapes that allow the air to move or flow over the cyclist more easily. Modern cars are also streamlined. Their smooth shapes make the air resistance smaller, which allows them to travel further on the same amount of fuel. Okay, let's look at forces in a little bit more detail now. In the first picture here, we're looking at balanced forces. Look at the green car. All the arrows are the same size, but pointing in opposite directions. So normal reaction is equal and opposite to weight. Thrust is equal and opposite to drag. Therefore, the overall force on this car is 0. All of these forces cancel each other out. We say that the forces are balanced and there is 0 net resultant force. Therefore, one of two things will happen to this car. It will either remain stationary or it will continue to move at constant velocity. You need to learn those two things for balanced forces. We call this Newton's first law. Now the second example is the parachutist, and we have an unbalanced force. In this example, the air resistance is bigger than the weight. You can see the up arrow is bigger than the down arrow. It should be twice the size. These forces are unbalanced. There is a resultant force. There are 3 possibilities here. Either the parachutist will speed up, which is called acceleration, or the skydiver will slow down, which is deceleration, or it will change direction. Three possibilities, and we call this Newton's second law. Okay, here are some more examples of balanced forces. So a balloon here is the upthrust is equal and opposite to the weight. The boat is floating, therefore the upthrust is equal and opposite to the weight, and the thrust is equal and opposite to drag. For the aircraft, lift equal and opposite to weight, thrust equal and opposite to drag, and we've already looked at this car in the previous slide. Okay, we're going to use Newton's second law. Newton's second law links three things together: resultant force, mass, and acceleration. There is a very simple equation. Resultant force equals mass times acceleration. You need to learn this. It will not be given to you in a formula book or sheet in the exam, and you are expected to learn this. There is a simple triangle to help you rearrange the equation. F at the top, M and A at the bottom. F stands for resultant force in newtons. Mass is M, must be in kilograms, and A is acceleration, and that unit is meters per second squared. This equation can be rearranged in three ways. F equals ma, A equals F over m, or m equals F over A. An important point to make here is that the force is the resultant force, so you will need to work out the resultant force first anytime you use this equation. And we're going to do some examples now so that you can see how we can use this. Okay, let's look at this example of a model car. This car has an unbalanced force acting on it. You can see the forward force is 60 and the backward force is 50. So the first thing we do is we work out the resultant force, which is very straightforward. It's 60 minus 50. The net force acting on this car, or the resultant force, is 10 newtons, and it goes in a forward direction. So that is the force we're going to use in the formula. Now we want to calculate the acceleration. We use A equals F over m. Acceleration equals resultant force over mass. So A equals 10 divided by the mass, which is 0.34, and the overall acceleration is 29.4 meters per second squared. So this car accelerates rapidly at first. Okay, here's another example of using Newton's second law. We can consider the space shuttle on its launch pad. Now at first the space shuttle is stationary on its launch pad, and then we fire up the engines and it launches upwards. We therefore need a larger upward force than we do downward force, and you can see here the unbalanced forces. We've got 1 million newtons going up at the top here, and we've got 500,000 newtons. That's the weight of the space shuttle pulling it down. These are large numbers. The space shuttle was a very large vehicle. We're going to use Newton's second law to calculate the acceleration of the space shuttle. So we need to work out first of all what the resultant force is. So we go 1 million minus 500,000. The resultant force is 500,000 newtons in an upward direction. Very important to also specify the direction. Remember, force is a vector. Direction is important. We're going to use this formula. Acceleration equals resultant force over mass. We're going to put the numbers in. Okay, the resultant force is 500,000. The mass of the shuttle, 50,000 kilograms. And we get an acceleration of 10 meters per second upward. Now, The unit is meters per second squared. Okay, so you'll notice that the resultant force is upward and the acceleration is also upward. Okay, this is a slightly different example. In some ways it looks similar to the previous one because the upward force is bigger than the downward force. However, there is a difference. The shuttle started on a launch pad and it wasn't moving, whereas the parachutist is already falling. Before they open their parachute, they're falling at great speed. So the parachute has the effect of slowing down the parachutist. So you have to think about the situation before you start doing the maths. But the maths is very similar in both situations. So we have an upward force of 1,200 and a downward weight of 1,000. So the resultant force is 200 newtons upwards. Now that does not cause the parachutist to accelerate upwards, but it does cause the parachutist to slow down. Use the same equation, A equals F over m. Use the resultant force divided by the mass, so it's 200 divided by 100, the mass is 100, look. And we get an acceleration upwards of 2 meters per second squared. Now I've used the word acceleration there, but of course it's causing the parachute to slow down, so it's a deceleration. It's causing the object to get slower. Right, thank you for listening, and I hope that you found this video helpful to your understanding of forces. I'd like you now, please, to go and look at the mini quiz on its learning. Thank you.